Remember Alice and Bob, the twins? Alice likes to stay home, whereas Bob is always rocketing off somewhere. Alice keeps track of Bob's proper time using the differential form of the time dilation formula. Let's manipulate the equation a little bit and substitute dx by dt for Bob's velocity. And we see that in Alice's coordinate system, the difference in Bob's squared coordinates yields the negative of Bob's squared proper time. If we had not suppressed the other two spatial dimensions, the metric equation may remind you of Pythagoras' theorem that you learned about in grade school. Just as observers in different orientations can use Pythagoras' theorem to agree upon the length of an object, the metric equation can be used in different reference frames to agree upon Bob's proper time interval. Before we move on from the Pythagoras theorem, there is one more thing about it I'd like to talk about. Imagine that instead of using Cartesian coordinates, someone comes along and decides to use polar coordinates. In that case, as can be seen from the diagram, he would measure ds squared to equal dr squared plus r squared d theta squared. Remember that in reality all these distances are supposed to be infinitesimal, so the relationship between dr squared, d theta squared, and ds squared becomes exact in that limit. Let's repeat these calculations using vector notation, because this will be instructive later. We see that ds equals dx ex plus dy ey, where ex and ey are unit vectors in their respective directions. They are also called basis vectors, because multiplying them by the change in their respective coordinates yields the length in that direction. Let's go ahead and find ds squared using these basis vectors. We have ds.ds equals this equation. Now let's expand it out. And now let's combine the two like terms in the middle. Comparing this equation with the original one, we see, as expected, that ex.ex equals 1, ex.ey equals 0, and ey.ey equals 1. We can summarize these results in matrix form. This matrix that specifies the dot products of the basis vectors of the coordinate system is called the metric tensor and is given the symbol G, as well as two subscripts that refer to the rows and columns of the matrix. To be clear, we can write out the components of G explicitly as follows: G00 equals 1, G01 equals 0, G10 equals 0, and G11 equals 1. So it is clear in Cartesian coordinates that the basis vectors have a size of 1. Of course we know that in Cartesian coordinates the basis vectors always point in the same direction. Ex points in the x direction, and ey points in the y direction, always. So let us look instead at polar coordinates to get a feel for basis vectors that change size and direction as we move through space. In polar coordinates, we have ds equals dr plus d theta e theta. Then ds.ds, or ds squared, is just the same as before, but replacing dx with dr, dy with d theta, ex with er, and ey with e theta. Comparing this equation with the distance equation in polar coordinates, we see that er.er equals 1, er.e theta equals 0, and e theta.e theta equals r squared. So this matrix tells us that er has a length equal to the square root of 1, which is 1, and e theta has a length equal to the square root of r squared, which is r. We also see that er and e theta are perpendicular to each other because their dot product is 0. But how do we determine how their orientation changes from this matrix? Let's bring our polar coordinate fellow down. Let's have him walk a distance ds equal to dr er plus d theta e theta. So Paul's r coordinate changed by an amount dr, and his theta coordinate changed by an amount d theta. Of course, he could also have reached the same new position by changing coordinates in the opposite order. That is, he could first change his theta coordinate by an amount d theta, and then change his r coordinate by an amount dr. Of course, he ends up in the same position as if he went the other way, since his coordinates are the same as if he went the other way. But wait a minute, his basis vector e theta has a length proportional to his r-coordinate, so the two d theta e thetas you see in the diagram must have different lengths. The one on the left should have length r d theta, because e theta has length r there. But the one on the right should have length d theta times r plus dr, because e theta has length r plus dr there. So let's shrink the one on the left a little bit to account for this difference. The difference in length is dr d theta, so let's mark that on the diagram. So in order for Paul to end up in the same position as before, we see that the basis vector ER must rotate through a certain angle in order to end up at the right spot. What is that angle? Well, ER has a length of 1, so the as yet unknown angle is given as dr d theta divided by dr, which equals d theta. So the basis vector ER must rotate through an angle d theta. If you are familiar with polar coordinates, you will have known this already, because that's how polar coordinates behave, namely that the r direction rotates with theta. But it is useful that we can discover this fact by analyzing the metric equation without having to be familiar with the coordinate system. Now the e thetas on the right and the left are not the same, so we should really change our notation there. If the basis vector on the left is e theta, then the one on the right is e theta plus a change, and that change is di e theta di r dr, since we have changed r by an amount dr, keeping theta constant between the two lower points. Similarly, the ER at the top is different from the ER at the bottom, so we should change our notation there too. If the basis vector at the bottom is ER, then the one at the top is ER plus a change, and that change is di ER di theta d theta, since we have changed theta by an amount d theta in the theta direction, keeping r constant between the two left points. So the distance represented by the green bar can be thought of in two ways. It can be thought of as the change in the vertical vector, or alternatively, it can be thought of as the change in the horizontal vector. The quantity dr d theta is actually a vector quantity. It is pointing in the theta direction, so we can use the theta basis vector to indicate this. However, the theta basis vector has length r, so we divide by r in order to give it unit length. The dr d thetas cancel in our double equation, and we are left with the result that 1 over r e theta equals di e theta di r, which also equals di er di theta. In this special case of polar coordinates, the basis vectors do not change in the er direction at all. But let's add that into our equation nevertheless, in order to better generalize our results. Let's break this up into two separate equations. We see that di e theta di r can be written in terms of the basis vectors, and di er di theta can also be written in terms of the basis vectors. In general, any coordinate partial derivative of the basis vectors can be written in terms of the basis vectors. The general equation implicitly defines a new quantity, which we call the Christoffel symbols. The matching indices are understood to be summed over. So in the case of polar coordinates, this equation would mean gamma theta mu nu e theta plus gamma r mu nu er. If we let mu equal r and nu equal theta, we can compare this equation directly with the first equation of the two above and obtain values for two of our Christoffel symbols. We see that gamma theta r theta equals 1 over r, and gamma r theta equals 0. As can be seen from the first two equations, the Christoffel symbols remain the same when we interchange the lower two indices. As a general statement, the Christoffel symbols are always symmetric in their lower two indices. The Christoffel symbols can be derived from the metric tensor components, as we just saw with polar coordinates. However, it would be useful to have a formula rather than having to draw out all the vectors as we did before. Let's start by taking the partial derivative with respect to x mu of both sides of the metric tensor definition. Now we replace the basis vector derivatives with our Christoffel symbol definition. Before we make the substitution, we see that we must change the mu to a beta, so we do that on both sides of the equation. Similarly, we change the nu to a mu on both sides of the equation. Finally, let's replace the alphas that are being summed over with nus, so as not to confuse them with the alpha in the above equation, which is not being summed over. Now let's put the e nu in front so that we can recognize the dot product of the basis vectors e alpha and e nu as g alpha nu, using our definition of the metric tensor above. The second term we handle much the same way. We use the definition of the Christoffel symbol, but we must change the mu's to alphas, the nus to mu's, and the alphas into another random letter, say nu, so as not to confuse them with the alpha that is being used already and not being summed over. Now let's move the e nu basis vector in front and recognize the dot product of the two basis vectors as g beta nu from the definition of the metric tensor. Our goal now is to solve for the Christoffel symbol. We will do this by making two new equations by permuting the indices alpha, beta, and mu. If alpha is changed to beta, beta changed to mu, and mu changed to alpha, we arrive at this equation. We need to permute the indices just one more time. Let beta change to mu, mu change to alpha, and alpha change to beta. Now we perform a little mathematical trick. We can add any two of these equations and subtract the third to arrive at an important result. On the right-hand side, some cancellations occur. We see that the first term cancels the last term because the Christoffel symbols are symmetric in their lower two indices. The fourth and fifth terms also cancel for the same reason. So we are simply left with the second and third term, which are the same due to the symmetry of the Christoffel symbols in the lower two indices. Now in Newtonian physics, an inertial object, such as Alice, will not accelerate, so dv by dt equals 0 for Alice. And in Cartesian coordinates, v has the three components dx by dt, dy by dt, and dz by dt. Different observers will disagree on dx, dy, and dz, but all will agree on dt in Newtonian physics, because time is an absolute quantity. In relativity, the same is true, as long as we use d tau for the time, where tau is the object's proper time. In that case, v can have three components, dx by d tau, dy by d tau, and dz by d tau. Different observers will disagree on dx, dy, and dz as before, but all will agree on the object's proper time d tau, just as before in Newtonian physics. In fact, in relativity, the time t, which has so far been left out of the velocity, is actually a fourth coordinate that different observers can disagree upon. So the Newtonian concept of velocity is extended to one more dimension whose component is dt by d tau. This four-dimensional velocity is denoted by u and is called the four-velocity. So the corresponding relativistic equation for inertial objects, dv by dt equals 0, is changed to du by d tau equals 0, where the four components of u in Cartesian coordinates plus time are dt by d tau, dx by d tau, dy by d tau, and dz by d tau. In a general coordinate system, we can write u as u alpha e alpha, where the e alpha are the basis vectors for that particular coordinate system. Let's now set du by d tau to equal 0, and see if we can discover the equations of motion for an inertial object. The first step is to make the substitution u tilde equals u alpha e alpha. By the product rule, this expands to u alpha dE alpha d tau plus e alpha du alpha d tau equals 0. Now the basis vectors are a function of the object's coordinates, whereas the object's coordinates are a function of the object's proper time. So we can write the first differential as di e alpha di x beta dx beta d tau. Of course, here the betas are summed over as usual. The quantity dx beta by d tau is u beta by definition, so let's make that replacement. Now it's time to use our definition of the Christoffel symbols to replace di e alpha di x beta. Let's change the mu's to alphas, the nu's to betas, and our alphas to nu's because they are being summed over and we don't want to confuse them with our other alpha that is not being summed over. Now we're ready to replace di e alpha di x beta in the equation. So let's do that. Now in the second term, let's replace the alphas with nu's, since they are just dummy indices that we are summing over. This way we can now factor out an e nu from both terms in the equation. Since e nu does not equal 0, this implies that u alpha gamma nu alpha beta u beta plus du nu d tau equals 0. Let's multiply this equation by g mu nu so that we can bring it in line with our definition of the Christoffel symbols. If we switch beta and mu in our Christoffel symbol definition, it matches the equation, and we can make the substitution. Let's remove the brackets and multiply through by u alpha u beta. Now the alphas and betas are being summed over, so switching alpha with beta in the second term doesn't change anything, so let's do that, thereby discovering that the second term is identical to the first term. Adding these two terms together yields the following result. Another thing to note is that dg alpha mu by d tau is equal to di g alpha mu by di x beta dx beta d tau by the chain rule, since g alpha mu is a function of the x beta, and the x beta are in turn a function of Alice's proper time. And here we replace dx beta by d tau with u beta, because that's the definition of the 4-velocity u beta. Let's now make this substitution into the above equation. Now in the first term, let's change the alphas, which are just being summed over, to nu's. And we'll change g nu mu into g mu nu, since they are the same because they're just the dot product of e nu and e mu, whose order doesn't matter. Now let's bring the last term closer to the first term so that we can notice something. We notice that d by d tau of g mu nu u nu is equal to dg mu nu by d tau u nu plus g mu nu du nu by d tau by the product rule. So we can make that substitution into the above equation. Finally, in the second term, let's change g beta alpha to g alpha beta for aesthetical purposes. This equation, called the geodesic equation, describes the motion of an inertial object such as Alice in Einstein's physics. The term geodesic is used because it can be shown to be equivalent to the shortest path between 2 points in spacetime. It is a nice result that the geodesic equation is equivalent to the 4-velocity u tilde being required to remain constant in proper time, analogous to the 3-velocity vector in Newtonian physics being required to remain constant in time for an inertial object. In our next video, we will use the geodesic equation to describe Alice's motion in Bob's accelerated Rindler coordinate system. Thank you for watching.